Dr. Nitisha Shrivastava. Welcome to the control system lectures. This lecture is in continuation with the Routh Hurwitz criterion to determine the stability of a system. Routh Hurwitz criterion determines the stability of a system as to yes or no, whether the system is stable or unstable, without having determining the value of the roots. This lecture is based on to determine the range of k or the value of k for which the system remains stable for a variable parameter k. In control system design problems, we can use this Routh Hurwitz criterion to check or to determine the range or the limits of k for which the control system will remain stable. This is used in simple control system design problems. It is frequently used for determination of the condition of stability of linear feedback control system. So, Routh Hurwitz criterion is used basically to determine the stability of a linear feedback control systems. Let us take one example here. This is a closed loop feedback system and we need to determine the range of k for which the system is stable. So, we have a forward path transfer function g of s. Forward path transfer function g of s is k divided by s into s square plus s plus 1 into s plus 4. So, this is g of s, and since it is a closed loop system having unity feedback, therefore, h of s is equal to 1. This is the closed loop transfer function. Closed loop transfer function g of s upon 1 plus g s h s is the closed loop transfer function. So, g s divided by 1 plus g s h s, we get the value of the closed loop transfer function, and the denominator of the closed loop transfer function, that is the characteristic equation of the given function. So, this is the characteristic equation, and opening the brackets, we get s raised to 4 plus 5 s cube plus 5 s square plus 4 s plus k. So, for this particular given closed loop feedback system, we get the characteristic equation. So, we are going to apply the Routh Hurwitz criterion to determine the range of k for the system to remain stable. So, Routh array is formed for the given characteristic equation s raised to 4 plus 5 s cube plus 5 s square plus 4 s plus k, 5 s square plus 4 s plus k. So, this is the characteristic equation. We are going to form the Routh array for this characteristic equation and determine the range of k for which the system remains stable. And the first step to determine to form the Routh tabulation is to write the first and the second row by using the coefficients of the characteristic equation. So, as can be seen, the highest order term here is s raised to 4. So, this part is for reference. This part is for reference. Now, this s raised to 4, s cube, s square, s 1 and s raised to 0 is for reference to know where the Routh tabulation should terminate. So, this is only for reference, and this is the actual tabulation. We have put the coefficient of the highest order term here as the first element of the first row, and then 5 is placed here, k is placed here. What remains? 5, this is 5, 4, this is 4, and if you do not have any term, it could be 0 or left blank. It is that there are no coefficients ahead. So, you can write it 0. So, this is the first step to form the first row and the second row of the Routh tabulation. Now, regarding the next row is obtained by multiplying 5 into 5, that is 5 into 5 minus 4 into 1, that is 5 into 5 minus 4 into 1 divided by 5. This is equal to 21 by 5. So, we get this element 21 by 5, and next element is obtained by 5 into k, that is 5 into k minus 1 into 0 minus 1 into 0 divided by 5, divided by 5, this is equal to k. So, this is the next element. We can continue ahead because neither we are coming across any special case, neither the first element of the first column elements are 0, neither the entire row is 0. So, we can go ahead with this. Next element is obtained by 21 by 5 into 4, 21 by 5 into 4 minus 5 k upon 21 by 5. So, this element, fourth row first element is obtained, and we can see that it is 21 by 5 into 0. So, this is minus 0, this will come out to be 0, and this is k, and this element is not there here. This is the formation of the Routh's tabulation for the given characteristic equation. As we had seen, what is the condition that the system remains stable from the Routh criterion? It is that the first elements, that is the elements of the first column, should have positive sign and there should not be any sign change. So, all the elements to have positive sign, for this table it is required that this element here in the first, second, third, fourth, fifth row, the first element in the fifth row is k, and for it to be positive its value should be greater than 0. So, one condition what we have obtained is with respect to this k, it is k should be greater than 0. For all the elements to remain positive, k should be greater than 0. We have an element k here also. We are not bothered about the remaining column elements. For Routh Hurwitz criterion, we are considering the first column elements of the Routh tabulation. Now, here we have a term k in the numerator. So, for this term, that is the fourth row first term, first element to be greater than 0, it is required that the numerator should be greater than 0. We have a denominator here and this is the numerator, numerator should be greater than 0. So, it is desired that for the system to be stable, 21 by 5 into 4 minus 5 k should be greater than 0. So, this is another condition. So, we can work out what will be the value of k for that. It is 84 by 5 should be greater than 5 k, that is 84 by 25 should be greater than k, or we can say that k should be less than 84 by 25. So, checking into the first column elements as related to Routh Hurwitz criterion, it is desired that all the values should be positive for the system to remain stable. Therefore, we come to a conclusion that for stability k should lie in the range between 0 and 84 by 25, and this is obtained from the condition that all the roots to lie, that is no roots to lie on the right half of the S plane, the first column element should be positive. Now, we can look at what happens if k is equal to 84 by 25. Now, if you substitute here k equal to 84 by 25, it happens that this part becomes 0. We can see here I have written the remaining elements 1 5 k, 1 5 k, 5 4 0, 5 4 0, 21 by 5 k, and there is no 21 by 5 k. Now, if this element becomes 0, so this element has become 0 when we put k is equal to 24, k is equal to 84 by 25. What we can understand from this is, when we are talking about the special cases, there are two special cases, that if the entire row becomes 0 or if the first element becomes 0. Now, we can see that this is the case of entire row becoming 0. We already have 0 values here existing. It means that now, if k is equal to 84 by 25, that range we have picked up from here, that if k is 84 by 25, the s raised to 1 row becomes completely 0. So, it becomes 0 means that is the system is marginally stable. There are roots on the j omega axis, and what are the roots on the j omega axis can be determined by using the auxiliary equation, that is the auxiliary polynomial. Auxiliary polynomial is obtained from that row which is preceding the row containing entirely zeros. So, here the auxiliary polynomial can be formed from the row which is preceding the s raised to 1 row. So, what will be the auxiliary polynomial? And 21 by 5 is for s square row. So, we write it as 21 by 5, it is a coefficient of s square plus skipping the next term. So, it becomes k equal to 0. 21 by 5 on k equal to 0 is the preceding row, and in this condition k is 84 by 25. So, this becomes 21 by 5 s square plus 84 by 25 equal to 0. So, once we determine what is the auxiliary polynomial, we can now determine what would be the value of the root which is lying on the j omega axis by solving the polynomial auxiliary polynomial, and this is how we obtain s equal to plus or minus j root 4 by 5. That means, for the value or for the system to remain stable, we determine the value of k should lie between 0 and 84 by 25. Now, this is for stability, but if the value of k is 84 by 25, that means the system is not less than 84 by 25, the value of k is not less than 84 by 25, but its value is exactly 84 by 25. It means that here the roots are lying on the j omega axis for k equal to 84 by 25, and that we have determined what are the roots of the polynomial when this value is 84 by 25, and that is obtained by auxiliary equation. So, that means for this condition the roots are lying on there are two roots which are lying on the j omega axis. So, the system is marginally stable for the value of k equal to 84 by 25. So, the frequency, what is the frequency of those sustained oscillations? The frequency of sustained oscillation can simply be obtained by s is equal to plus or minus, this is j frequency. So, that frequency is root of 4 by 5 radians per second. Another example we can take up to understand how to determine the value of k for the system to remain stable. The open loop transfer function has a unity feedback system. This is the open loop transfer function. Find the limit of k so that the closed loop system is absolutely stable. Now, what is g of s? That is the open loop transfer function. So, g of s is this value, since it is an open loop transfer function, and we have unity feedback system. So, unity feedback system means h of s is 1. So, Routh Hurwitz criterion is tested on the characteristic equation of the closed loop transfer function. So, finding the closed loop transfer function, C of s upon R of s is G of s upon 1 plus G s H s. So, characteristic equation is 1 plus G s H s equal to 0, the denominator of the closed loop transfer function, that is the poles of the closed loop transfer function is determined, and this is the characteristic equation, s cube plus 6.5 s square plus 10 s plus 10 k. Now, we are going to test the stability of the given condition, given system by using Routh Hurwitz criterion. So, this is the characteristic equation, and forming the Routh table, the first step is to place the coefficients. Again, this is for reference, that where will the Routh tabulation terminate, where will the Routh array terminate. So, we write this for reference. Here the coefficient of s cube is 1 and this is 10 here replaced, and this 6.5 and 10 k, that is 6.5 and 10 k. Forming the next elements, it is 6.5 into 10 minus 10 k divided by 6.5 is this element, and correspondingly this is 0. How do we get this value? It is the first element multiplied by 10 k minus 0 upon the first element here. So, we get 10 k and the remaining are 0. The question here is to determine the absolute stability, the value of k for which the system is absolute stable. So, for absolute stability, what is the Routh condition here? For the roots not to lie on the right half of the S plane, the first element, that is the first column element, should all have a positive sign. So, if all the elements are having positive sign, there are no roots in the right half of the S plane. It means that there are two elements having the term k. Here we can see that 10 k to be positive, it requires that k should be greater than 0, and in this 65 minus 10 k should be greater than 0. For the first element of the third row to be positive, the numerator 65 minus 10 k should be greater than 0. So, 65 minus 10 k, that is 65 should be greater than 10 k. It means that 6.5 should be, k should be less than 6.5. So, we have got two conditions here, one that k should be 0 and other that k should be less than 6.5, and this is obtained, this condition is known through Routh Hurwitz criterion, that is the condition is the first elements of the column, first column should be all positive, and therefore, for closed loop stability, the limit of k is that it should lie between the range 0 to 6.5. So, for absolute stability, k should not go beyond 6.5, not even 6.5. If the value of k is 6.5, then the system will become marginally stable, but here we have to determine what would be the value of k for absolute stability. So, the value of k for absolute stability is 0, less than k and less than 6.5. Thank you.